Welcome to Robotics Foundations 2. I'm Bruno Siciliano and Professor of Robotics in the Department of Electrical Engineering and Information Technology at University of Naples, Federica II. In the first part of the course, you learn about modeling through the kinematics, differential kinematics, statics, and dynamics. In the second part of the course, you will be learning about planning and control. And if you read the subtitle of the textbook that we'll be adopting for this second part course, is Modeling, Planning, and Control. So we'll be covering the contents of Chapter 4, Chapter 5, 8, 9, 10, and 11 in this course. So the first problem that we'll be solving is the so-called trajectory planning problem. It's worth distinguishing between path and trajectory. Path concerns only with the geometric description of the motion, whereas by trajectory we mean the assignment of a time law along the geometric path. Now, we'll be solving two kinds of problem, the point-to-point motion and the motion through the sequence of points. And in doing this, we also want to be able to account for the dynamic constraints given by the torques to be exerted along the motion by the robot manipulator. How do we want the trajectory planning algorithm to be? We want this trajectory planning algorithm to be simple in terms of a reduced number of parameters. So, for instance, the initial point and the final point, eventually the intermediate points. We want an analytic expression, an interpolating function for the time law. We specify the final time, although in industrial setting this is not usually allowed for the user. And also we want to be guaranteeing the continuity of velocity and acceleration along the path. We can solve the problem in the joint space, as we'll be doing in this unit, and in which typically we solve the inverse kinematics and then we generate the reference for the control schemes in joint space. Otherwise, in the second unit, we'll be solving the problem in the operational space, in which we'll be accounting for the natural constraints like object, singularities, redundancy, and so forth. So let's start with the problem of the point-to-point motion, and I want to move the joint from an initial position Qi to a final position Qf. And I want the generate trajectory to be smooth, and also I want to guarantee the continuity of velocity and accelerations besides the position, and more importantly, I want that the computational is simple, so the algorithm must be computationally cheap. Let's start with the point-to-point motion. If we want to interpolate from Qi to Qf, we can use a linear blend, but then we won't be able to specify the velocities. So if we want to specify the initial and final velocity, the solution goes through adopting a cubic polynomials with 4 coefficients. So we have a system of 4 equations in 4 unknowns, which can be simply solved to compute the interpolating motion. What if we want to interpolate and guaranteeing also a given value of initial acceleration and final acceleration? The order of the polynomial grows from 3 to 5, and with the quintic polynomial, 6 coefficients, 6 unknowns, so in 6 equations we can solve the problem. In the industrial setting, there is a technique which is computationally cheaper, and this consists in adopting the trapezoidal velocity profile. It's a very simple concept. You accelerate to the top of your velocity, then you have a cruise, and then you have a deceleration. And the actual mathematical way to solve the problem is to consider an acceleration time, a symmetric deceleration time duration of Tf minus Tc, and then you have 2 techniques. One is to specify the maximum value of acceleration, which of course must be greater or equal to 4 times the total stroke divided by the square of the final time, or specifying the maximum value of velocity, which in this case must be limited between the total strokes time divided by Tf and 2 times the total stroke divided by Tf. This is fine for solving the point-to-point motion. Let's consider now the motion through a sequence of points. We'll be presenting 4 techniques. The first technique is basically to interpolate through a sequence of points and in specifying the values of velocities. But you may wonder though, why not to consider a polynomial of order n minus 1 to solve this problem? Because this will be becoming computationally too heavy, and also the degree of accuracy of the solution will decrease as the order of polynomial increases, and if you want to change 1 point in the sequence you have to recompute everything. So let's consider n minus 1 cubic polynomial to interpolate, and just we specify the values of the velocities at the intermediate points, just guaranteeing continuity. So this is technique number 1. Technique number 2, we can compute those velocities as the simple average of the average sum of the velocities in the previous time lapse and in the subsequent time lapse. We can compute this average, and if the two signs of the velocities are disagree, then we just set 0 as a value. Now, this is to guarantee continuity of velocity, but you're also concerned with continuity of accelerations. And this brings us to the third solution, which is the so-called splines. What is a spline? Spline is a sequence of interpolating polynomial to the sequence of points which give a smooth trajectory. Now, if you have n points, you can have 4 coefficients for each polynomial and n minus 1 polynomial. Then if you want to specify the initial and final acceleration, then you could use a 4th order polynomial. But this would lead you to an asymmetric solution. So basically, other than considering this solution, we introduce 2 virtual points. We're not concerned with the actual position of those points, but we're just concerned with the time instant. And if we recompute the whole system, we can have a square system of 4n plus 4 equations in 4n plus 4 unknowns. But the actual system to solve, it can be shown to be of order n, in which, on top of this, the system matrix has a 3-diagonal band. So you can use a simple Gaussian elimination technique to solve and find the solution. The fourth technique consists in instead of requiring the passage through the path points, we can have a passage through the via points. And these via points can be achieved in 2 ways. One way is to have a technique of a linear interpolation with parabolic blend, in which the acceleration around the via point is computed as the average of the two as the sum of the average sum of the 2 velocities before and after the point. Or there is an even simpler solutions, just resorting to the technique in industrial setting, which consists in anticipating the generation of the second trapezoidal velocity profile in such a way as to gain time and to guarantee the fly motion through the via points. The final topic that we'll be considering in trajectory planning in the joint space is concerned with the dynamics of the robot manipulator. You remember the dynamic model for the first part. If we look at the term containing the velocities, I'm speaking about the Coriolis centrifugal terms, that term is quadratic in the velocity. So the solution consists in choosing a time warp, the new function r as a function of t, so q becomes a function of t through this r function, and if we recompute the dynamic model with this new term, we can show that both the acceleration term and the velocity term can be pointed out as a function of this new function r. So if we choose this function as a linear function, that is rt as c times t, we can recompute the torque in terms of the square of this parameter. And this technique can be used to slow down the trajectory in a kind of automatic wave. So this is like dynamic scaling with c greater than 1, or could also be used to accelerate the trajectory in case the torques are not exceeded. So with the c smaller than 1, we can speed up the trajectory up to reaching the time limit. So these are the solutions for the trajectory planning in the joint space. In the next unit, you'll be learning about solving the same problem in the operational space.